Look up at the night sky, past the familiar constellations and the faint glow of the Milky Way, and know this: just 2.5 million light-years away drifts a colossal spiral galaxy, our closest major galactic neighbor, Andromeda. To the unaided eye, it's a smudge of light, a whisper in the cosmos, but hidden within its immense, silent halo, a vast, mysterious region stretching over 1 million light-years, are secrets that defy imagination. We've long been fascinated by Andromeda's core, its sweeping arms, its brilliant clusters, yet some of its most astonishing wonders aren't in the bright, crowded center, but in the lonely, dark outskirts, drifting like cosmic ghosts in the void. What if I told you astronomers have recently uncovered 30 strange objects glowing, puzzling, and utterly unexpected scattered throughout this enormous halo? Some may be orphaned star clusters wandering without a home. Others could be the faint remnants of ancient galaxies torn apart and absorbed eons ago. A few might even be something entirely new, celestial phenomena we don't yet have a name for. Each one tells a piece of a story billions of years in the making, a narrative of collision, survival, and mystery on a scale almost too grand to comprehend. This is not just a tour of distant lights, it's a journey to the edge of understanding, a chance to explore the unknown lurking right next door in our cosmic neighborhood. Together, we'll unravel the clues behind these enigmatic objects, venturing into the shadowy reaches of Andromeda's halo to uncover what they are, how they got there, and what they reveal about the life and death of galaxies. So settle in and open your mind to the possibilities. You're about to witness one of the most thrilling astronomical detective stories ever told. Our journey begins with the very first of these halo objects, one that astronomers have nicknamed the Andromeda Giant. It sits far from the galaxy's bright center, a solitary behemoth adrift in the sparse outer darkness. Initially catalogued as just another globular cluster, a tight, spherical swarm of stars, it quickly became clear this object was anything but ordinary. Standard clusters might contain a few 100,000 stars. This one is on an entirely different scale, boasting a staggering estimated mass millions of times that of our own Sun. Its sheer size immediately placed it outside every known model for how such clusters are supposed to form, but the surprises didn't stop with its mass. When researchers pointed their most powerful instruments toward it, they found its stellar population was bizarrely mixed. Unlike the uniform, ancient stars found in a typical globular cluster, the Andromeda Giant contains a strange cocktail of stars of vastly different ages and metallicities. Some stars are incredibly old and metal-poor, relics from the very early universe. Others appear surprisingly young and metal-rich, suggesting a much more recent period of star formation. This combination is virtually unheard of and points to a far more dramatic origin story than a simple cluster. The leading theory is that we are not looking at a cluster at all, but the ghost of a galaxy. Astronomers propose that the Andromeda Giant is the stripped bare core of what was once a dwarf galaxy, a small system that wandered too close to the immense gravitational pull of Andromeda billions of years ago. In a process called tidal disruption, the larger galaxy would have slowly shredded the dwarf, pulling away its outer stars and dark matter, leaving behind only its dense, stubborn heart to continue orbiting in the halo. This celestial fossil, a galactic nucleus surviving long after its original body was consumed, offers us a direct glimpse into the violent, cannibalistic history that has shaped Andromeda into the giant we see today. Moving from that single, dense fossil of a galaxy, we now shift our gaze to a structure of an entirely different nature, one not confined to a single point but stretched across the void like a cosmic brushstroke. This is Halo Streamer Alpha, a breathtaking river of stars flowing through the darkness of Andromeda's halo. If the Andromeda Giant is a solitary monument, this streamer is a highway of ancient light, a delicate ribbon weaving a story of destruction and gravity on an epic scale. Discovered not as a concentrated smudge but as a subtle, extended trail of stars in ultra-deep imaging surveys, Halo Streamer Alpha is a tidal stream. Its very existence is a direct and beautiful consequence of galactic cannibalism. It began its life as a small satellite galaxy, perhaps not too different from one of the dozens of dwarf galaxies that still orbit Andromeda today. Billions of years ago, this doomed system ventured too close. Andromeda's immense gravity, its tidal force, acted like a cosmic hand, first stretching the smaller galaxy and then relentlessly pulling it apart. The process was slow and violent, a gravitational spaghettification that scattered the dwarfs' stars into long, looping arcs that continue to orbit within the halo. What we see today is the glittering debris of that ancient collision, a stellar corpse forever tracing the path of its own demise. The clues to its origin are written in the light of its stars. Spectroscopic analysis reveals a profound secret. These stars are incredibly metal-poor. In astronomical terms, metals refer to any element heavier than hydrogen or helium. The first stars in the universe were composed almost entirely of these two primordial elements. They forged the first metals in their cores and then scattered them across the cosmos in violent supernova explosions. A population of stars with very low metal content is therefore a telltale sign of extreme age, indicating they formed from pristine, early universe gas. The stars in Halo Streamer Alpha are just that, ancient relics from one of the universe's first generations of galaxies. This streamer isn't just the remnant of any disrupted galaxy. It's the ghost of a true pioneer, one of the original building blocks that merged to form the majestic Andromeda we see today. But this river of stars is more than just an archaeological site. It's a powerful tool for modern astronomy. Because the stars in the stream are all moving together along a predictable orbital path, they act as perfect tracers for the invisible force that guides them, Andromeda's gravitational field. By meticulously mapping the stream's exact shape, width, and density, scientists can perform a technique called galactic cartography. The subtle twists and gaps in the stream, the very way it flows, reveal the distribution of dark matter throughout the halo. Dark matter, which neither emits nor absorbs light, reveals its presence only through its gravitational influence. This stellar stream, therefore, is like a probe sent out to chart the invisible geography of the galaxy, allowing us to see the unseen and measure the distribution of the mysterious substance that makes up the vast majority of Andromeda's mass. While the halo is filled with the ghosts of entire galaxies, it also contains the remains of individual stars that met spectacular ends. Drifting through this immense darkness is one of the most extreme objects ever identified, a lone neutron star streaking through the halo at a staggering velocity. This isn't a star in any sense we usually imagine. It's the city-sized, impossibly dense core of a once massive star that exploded in a supernova, a cosmic bullet now traveling alone through the void. Its journey began with a cataclysm, when a star many times more massive than our Sun exhausts its nuclear fuel. Its core collapses under its own immense gravity. This collapse triggers a titanic rebound explosion, a supernova, that blasts the star's outer layers into space, leaving behind an ultra-compressed remnant. If the core is massive enough, it will collapse into a black hole. But if it's just below that threshold, it forms a neutron star, an object so dense that a single sugar cube-sized piece of it would weigh as much as a mountain. This particular neutron star, however, wasn't found nestled within the cloudy debris of its supernova remnant. It was discovered completely isolated, a solitary point of intense X-ray emission racing through the quiet halo, far from any trace of the explosion that created it. The key to its lonely existence is its unbelievable speed. Neutron stars can receive a powerful kick from a supernova explosion. If the explosion is even slightly asymmetrical, imagine a titanic cosmic cannon firing rather than a perfectly spherical balloon popping. It can launch the newborn neutron star at hundreds of kilometers per second. This object is a prime example of that phenomenon, moving so fast that it quickly escaped the gaseous shell of its own supernova remnant and eventually the disk of its host galaxy entirely, catapulting itself into the intergalactic wilderness of the halo. It's a runaway celestial object, a testament to the violent and chaotic forces unleashed during a star's final moments. What allows us to detect this tiny, dark object from such an immense distance? The answer lies in its powerful X-ray glow. Isolated neutron stars are often invisible in optical light, especially after they've cooled over millions of years. But this one is what astronomers call an isolated cooling neutron star. Its surface, still searingly hot from the energy of its formation, emits intense thermal X-ray radiation. By analyzing this X-ray spectrum, scientists can effectively take the temperature of this stellar corpse, which in turn tells us about its age and composition. Furthermore, as it rockets through space, its powerful magnetic field, trillions of times stronger than Earth's, can interact with any stray particles in the halo, creating additional detectable emission. This lone wanderer, therefore, acts as a unique probe, not only telling the story of its own violent birth, but also providing clues about the density and nature of the seemingly empty space within a galactic halo. Yet these gravitational mirages are not the only clues pointing to this ghostly presence. Another line of evidence comes from the motion of the stars we can see within that region of the halo. When astronomers tracked the velocities of these visible stars, they found they were moving in ways that simply didn't make sense if the only gravitational pull was from the stars and gas around them. Their speeds and trajectories implied they were orbiting an immense, unseen mass, a gravitational anchor holding them in place that emits no light of its own. This independent confirmation, the dance of the visible pointing to the presence of the invisible, solidified the conclusion that this was a substantial clump of dark matter, a hidden node in the cosmic web. So why is this considered a pure dark matter substructure? In most galaxies, dark matter and ordinary matter are intertwined. Where there are dense collections of stars and gas, there is usually an even larger halo of dark matter. But in this case, deep imaging reveals no associated starlight, no glowing gas clouds, no clusters, nothing to indicate the presence of any significant amount of normal matter. It appears to be a self-contained knot of dark matter that has managed to avoid collecting the baryonic material needed to spark star formation. It is a cosmic phantom, a gravitational entity that exists almost entirely in the shadow realm of dark matter, making it an exceptionally rare and valuable laboratory for study. The existence of such a pristine object has profound implications for our understanding of the universe on the grandest scale, specifically for the lambda cold dark matter model, which is the prevailing theoretical framework describing the cosmos's evolution. This model predicts that the dark matter halo of a large galaxy like Andromeda should be littered with thousands of smaller subhalos, clumps of dark matter that never manage to attract enough gas to form bright galaxies. For years, a troubling discrepancy called the missing satellites problem persisted, where simulations predicted far more of these small dark matter clumps than the number of observed dwarf galaxies. The discovery of this pure dark matter clump provides a compelling solution. The satellites aren't missing at all. They are everywhere. We just couldn't see them because they contain no stars. This object is a direct detection of one of those long-predicted starless subhalos, a vital piece of observational evidence that helps reconcile theory with reality and confirms that our model of the universe's structure is fundamentally on the right track. Drifting in the profound silence between stars, we find an object of haunting beauty, a planetary nebula, but one like no other. This cosmic jewel, known to researchers as Object 5, hangs in the void of Andromeda's halo, a perfect sphere of luminous, expanding gas. It's the final, brilliant sigh of a dying star, a sun-like star that reached the end of its life and gently blew its outer layers into space. What makes this particular nebula so strange isn't its life cycle, but its location. These glowing shells are typically found within the bustling disks of galaxies, where stars are born and die together. To find one all by itself, adrift in the lonely galactic halo, is like discovering a single, perfectly preserved soap bubble floating miles above the Earth, far from the child who blew it. It simply doesn't belong there, and its presence tells a story of cosmic exile that began billions of years ago. The key to unraveling this mystery lies in the light the nebula emits. When astronomers train their spectrographs on this glowing shell, they don't just see a pretty cloud of gas, they read its chemical composition like a cosmic history book. The results are startling. The gas is remarkably deficient in what astronomers call metals, elements heavier than hydrogen and helium. This is a crucial clue. Stars act as factories, forging these heavier elements in their cores through nuclear fusion. When they die, they seed their surroundings with these newly created metals, enriching the next generation of stars. A star that is metal-rich is typically young, having formed from gas that was already polluted by the deaths of its ancestors. A metal-poor star, however, is ancient, a relic from a time before this cosmic recycling program had really begun. The profound lack of metals in this planetary nebula points directly to the identity of the star that created it. This was no ordinary sun. It was a star from the universe's first generation, a celestial senior citizen that formed over 10 billion years ago from the pristine, unpolluted hydrogen and helium that filled the cosmos after the Big Bang. It lived an incredibly long, quiet life, faithfully burning its fuel for eons while the universe evolved around it. Its home was likely one of those ancient dwarf galaxies, a primordial building block that was consumed by the growing Andromeda galaxy in the distant past. When this star finally reached its end, it did not die surrounded by its stellar siblings in a bright galactic disk. Instead, it exhaled its metal-poor, ghostly shroud into the dark, quiet halo, a solitary monument to a galaxy that no longer exists. This intergalactic planetary nebula is more than a beautiful anomaly. It's a direct probe into the early chemical conditions of the universe. By studying its unique composition, scientists can effectively peer back in time to an era before most heavy elements even existed. It provides a pristine benchmark, a snapshot of the raw material from which the very first stars were made. Furthermore, its isolated location confirms a dramatic galactic history. Its presence in the halo means it was ripped from its original home during a galactic merger, and then flung into the void where it drifted for billions of years before its final, luminous act. This glowing shell is therefore a dual relic, a fossil of a long-dead star and a fossil of a long-dead galaxy, its gentle light illuminating two different chapters of cosmic history at once. Now let's turn our attention to a true cosmic speedster, a star on a one-way ticket out of the galaxy. This isn't just a fast-moving object. This is a hypervelocity star, an object traveling with such immense speed that it has achieved escape velocity from Andromeda itself. Unlike the runaway neutron star propelled by a supernova kick, this is a sun-like star, and its incredible journey appears to have begun not with an explosion, but with a gravitational catapult lurking at the very heart of its home galaxy. The concept of a star moving fast enough to leave its galaxy is almost difficult to grasp. The gravitational pull of a giant spiral like Andromeda is immense, binding billions of stars to it. To break free, an object needs a truly phenomenal source of acceleration. When astronomers first measured the velocity of this particular star, designated Object 6, the numbers were staggering. It's racing through the halo at over 1,000 kilometers per second. At that speed, you could travel from Earth to the Moon in under 7 minutes. This star isn't just drifting, it's fleeing, hurled outward with enough force to eventually leave the galactic neighborhood forever, destined to spend eternity wandering the bleak, empty space between galaxies. So where could such an incredible force originate? All evidence points a gravitational slingshot of almost unimaginable power. The most compelling theory traces this star's path backwards, and its trajectory seems to lead directly to the chaotic core of the Andromeda galaxy. At the center of Andromeda, as in our own Milky Way, lies a supermassive black hole, a gravitational titan with a mass equivalent to millions of suns. The environment around such a monster is a violent maelstrom of forces where the laws of physics are pushed to their extreme. The leading explanation for our hypervelocity star involves a rare and unfortunate cosmic dance. Most astronomers believe it was once part of a binary star system, two stars happily orbiting each other as they journeyed through the galaxy. Billions of years ago, this binary pair wandered too close to the central black hole. The immense gravity of the black hole would have violently disrupted their orbit, capturing one star while violently flinging the other away at an astronomical speed. This mechanism, known as the Hill's mechanism, turns a binary system into a cosmic catapult. One star is condemned to orbit the black hole, or perhaps even be consumed by it, while its partner is ejected at a significant fraction of the speed of light, sent careening out of the galaxy on a new, solitary path. This object acts as a unique and powerful probe, offering us indirect but compelling evidence for the presence and behavior of Andromeda's central black hole. By studying its speed and trajectory, we can better understand the dynamics at play in the galactic nucleus. Each hypervelocity star we discover adds another data point, helping us map the gravitational influence of the supermassive black hole and even estimate its properties. Furthermore, the very existence of such stars tells a story about the history of the galactic center, suggesting that these dramatic three-body interactions, while rare, have been happening for eons. As this star continues its journey, it carries with it the chemical signature of its birthplace. Its composition is a time capsule from the central regions of Andromeda, allowing us to study the makeup of stars that form in that unique, intense environment without having to peer directly into the bright and crowded chaos of the galactic core. This lone traveler, ejected in a moment of cosmic violence, now serves as a silent ambassador, carrying secrets from the heart of its galaxy out into the darkness for us to find and decipher. Among the faintest and most ancient denizens of the halo, two objects stand out not for their brilliance but for their profound obscurity. Designated simply as Object 7 and Object 8, these are ultra-faint dwarf galaxies, twin ghosts clinging to the outermost fringes of Andromeda's gravitational domain. To call them dim is a monumental understatement. Each contains so few stars that their combined light is less than 1,000th of the light from our Milky Way's full moon. They are not merely hard to see, they are on the very threshold of detectability, requiring the most powerful telescopes and painstaking analysis to pull their faint signal from the blackness of space. Their feeble starlight, however, belies an immense and hidden power. The true nature of these dwarfs is revealed not by the stars we can see, but by the way those stars move. When astronomers measure the velocities of their individual suns, they discover something astonishing. These stars are orbiting at speeds that should be impossible. If the only gravity present was from the visible stars themselves, they should have long since drifted apart. The fact they are moving so quickly means they are held together by an immense, unseen gravitational anchor. The conclusion is inescapable. These ultra-faint dwarfs are composed almost entirely of dark matter. For their size, they are among the most dark matter-dominated objects in the entire universe, with this mysterious substance making up over 99% of their total mass. This incredible dark matter content makes them perfect cosmic time capsules, pristine relics from the universe's infancy. The stars within them are among the oldest ever observed second-generation suns that formed from gas enriched by the very first supernova. They are incredibly metal-poor, their composition almost untouched by the cycles of star birth and death that polluted larger galaxies. Studying these dwarfs is like opening a window to a time over 13 billion years ago, allowing us to directly observe the properties of the universe's first small galaxies, the basic building blocks that merged to form giants like Andromeda. Their mere existence, surviving for so long on the edge of a galactic giant, is a story of quiet resilience. Their remote location in the halo's vast expanse saved them from the violent tidal forces that shredded and consumed their brighter, more central siblings. While other dwarf galaxies were torn apart and absorbed into Andromeda's disk, these faint, dark matter-rich ghosts have endured, orbiting silently for eons. Their survival offers a crucial clue to a long-standing cosmic puzzle, the missing satellites problem. Computer simulations of dark matter predict that thousands of small clumps should orbit a large galaxy, yet we observe only dozens of bright dwarf galaxies. Objects 7 and 8 and others like them demonstrate that the satellites aren't missing at all. They are everywhere, we just couldn't see them because they are too faint. These twin ultra-faint dwarfs are the visible tip of a vast dark iceberg, representing the countless dark matter subhalos that fill the galactic halo, just as the theories always said they should. Deep within the halo's sparse expanse, we find an object that defies simple visual observation, one that reveals itself not in visible light but through a powerful natural broadcast. This is Object 9, a colossal cloud of water vapor on a truly cosmic scale, but it is behaving in a way that transforms it from a simple gas cloud into a brilliant astronomical beacon. It's known as a megamaser, a name that combines maser, which stands for microwave amplification by stimulated emission of radiation, with the prefix mega to signify its incredible power. In essence, this distant cloud is functioning like a natural laser, but instead of producing a beam of visible light, it generates an intense, focused emission of microwave radiation. The process that creates this phenomenon is both precise and spectacular. It begins with the energy from a phenomenal cosmic engine, an intense burst of star formation, or perhaps the active nucleus of a galaxy. This energy pumps the water molecules within the cloud, elevating them to a higher energy state. Then, when a passing microwave photon of the right frequency strikes one of these excited molecules, it triggers a chain reaction. The molecule drops to a lower energy state and releases an identical photon, traveling in the same direction and in perfect phase with the first one. This is the stimulated emission. Billions upon billions of these events occur in sync, amplifying a weak signal into an immensely powerful, coherent beam of microwave light that can travel across millions of light years without significantly dispersing. This makes megamasers one of the brightest point sources in the radio sky, allowing us to detect them from staggering distances with incredible clarity. For astronomers, this powerful signal is far more than a cosmic curiosity. It is an exquisitely precise tool. The microwave emission from a water megamaser occurs at a very specific known frequency. As this signal travels through the expanding universe, its wavelength gets stretched or redshifted. By measuring precisely how much the frequency has shifted from its known value, scientists can calculate the cloud's recessional velocity with extraordinary accuracy. This allows them to pinpoint the object's location within the halo and determine its motion relative to Andromeda itself. Furthermore, because the emission is so coherent and bright, very long baseline interferometry can be used to map the maser spots within the cloud with sub-millisecond resolution, an incredible level of detail that is otherwise impossible to achieve at such distances. So what cosmic engine is powerful enough to pump this natural laser? The leading explanation points to a massive, hidden starburst region, a veritable factory for new stars, shrouded within a dense cocoon of gas and dust. This stellar nursery is likely embedded within a smaller, gas-rich satellite galaxy or a massive cloud that Andromeda is currently in the process of consuming. Within this dusty envelope, hundreds or thousands of massive, hot stars are being born in a ferociously rapid burst of activity. The intense ultraviolet radiation from these newborn stars is the energy pump that excites the surrounding water molecules, powering the megamaser and causing it to shine so brightly in its specific radio frequency. This makes the megamaser cloud a brilliant keyhole, allowing us to peer directly into an environment that would otherwise be completely opaque. Visible light from the burgeoning star cluster is utterly absorbed by the thick, natal dust, rendering it invisible to optical telescopes. But the microwave emission from the water molecules punches straight through that dust, unmistakably signaling the violent and fertile activity happening within. The discovery of this megamaser, therefore, did more than just add another strange object to our list. It unveiled an entire hidden chapter of Andromeda's ongoing evolution, revealing a region of intense star birth happening in the shadows of the halo, a testament to the dynamic and unfinished nature of galactic growth. Now we turn our attention to a different kind of wanderer in the halo, one that moves to the beat of its own drum. This is Object 10, a colossal cloud of primordial hydrogen gas so vast it contains enough material to form millions of new stars. But its true strangeness isn't just its size, it's the path it takes. While the vast majority of material in Andromeda, the stars, the gas, the dust rotates in a single, coherent direction, this enormous cloud is doing the exact opposite. It's a counter-rotating anomaly, a cosmic rebel swimming against the current of the entire galaxy. The existence of such a massive object moving in retrograde motion is a huge clue to its origin. It is incredibly difficult, if not impossible, for a structure this large to form naturally within a galaxy and immediately start moving backwards. The prevailing motion of a spinning galaxy is like a whirlpool. Everything gets swept up in the dominant direction. For a cloud of this scale to be orbiting in reverse strongly suggests it did not originate within Andromeda itself. Instead, the most compelling theory is that this is an extragalactic visitor, a cloud that has fallen into the halo from intergalactic space. It could be a remnant of the cosmic web, a filament of pristine gas that was drawn in by Andromeda's immense gravity, or perhaps the last gaseous remnant of a small galaxy that was completely torn apart long ago. Its stars scattered while its gas survived this long journey. This counter-rotation has profound implications for the cloud's ultimate fate. Because it is moving against the flow, it is on a direct collision course with the gas in Andromeda's own disk. This isn't a gentle merger, it's a high-speed, head-on crash. When this cloud eventually plows into the galaxy's gaseous plane, it will trigger a spectacular burst of turbulence and compression. The immense pressure from this collision will violently shock the gas, catalyzing the birth of countless new stars in a brilliant wave of stellar formation. We see evidence of this process in other galaxies, where accreted gas sparks the creation of dazzling blue rings of young, hot stars. Beyond this fireworks display, the cloud represents a vital delivery of raw materials. Galaxies like Andromeda gradually consume their gas reserves to form new stars. Without a fresh supply, star formation would eventually sputter and stop, leading to a stagnant and aging galaxy. This counter-rotating cloud is a massive shipment of fuel, a billions of years worth of hydrogen gas that will eventually replenish Andromeda's dwindling reserves. Its accretion is a key part of the galaxy's life cycle, a demonstration of how galaxies continue to grow and evolve not just by consuming stars, but by gathering the primordial gas that will become the stars of tomorrow. This rebellious cloud, therefore, is not a destroyer but a provider, its contrary motion setting the stage for a future epoch of cosmic renewal and birth within our galactic neighbor. Now we venture into the silent aftermath of one of the most violent events a galaxy can experience. drifting in the halo is a vast, ethereal structure known as Object 11, a colossal lobe of faint radio emission that astronomers have nicknamed the ghost of a quasar. To the eye, it is utterly invisible, but to radio telescopes, it glows as a testament to a cataclysm of almost unimaginable ferocity that occurred billions of years in the past. This structure is the lingering echo of a time when the supermassive black hole at Andromeda's heart was not the relatively quiet giant it is today, but a raging behemoth, an active galactic nucleus that shone with the light of 1,000 galaxies as it feasted on cosmic matter. The process that created this ghost began deep within the galactic core. When a supermassive black hole actively pulls in vast quantities of gas, dust, and even stars, the material doesn't fall straight in. It forms a searingly hot, swirling disk of plasma called an accretion disk, heated to millions of degrees by immense friction and tidal forces. As particles in this maelstrom are accelerated to near light speed, powerful magnetic fields channel some of them away from the poles of the black hole, shooting them out into space in the form of tightly focused, opposing jets. These jets, composed of relativistic plasma, can travel for hundreds of thousands of light years before they finally slam into the tenuous gas that exists in intergalactic space. When this collision happens, the jet material billows out, forming massive, balloon-like structures on either side of the galaxy radio lobes. What we see as Object 11 is one of these lobes, a fossilized bubble of ultra-hot gas that has been slowly fading for eons, its energetic particles still spinning in magnetic fields and emitting a faint radio whisper. The sheer size and age of this structure are what make it so scientifically valuable. The lobe is immense, stretching across tens of thousands of light years. Its current location, far out in the halo, and its faintness tell us that the eruption that created it happened a very long time ago, likely over 200 million years in the past. This allows us to piece together a timeline of Andromeda's activity. We now know that its active quasar phase was not a continuous state but a dramatic, episodic event, probably triggered by a major influx of fuel, such as the collision with a large gas-rich galaxy or the sudden disruption of a giant molecular cloud that drifted too close to the core. The ghost lobe is a direct measurement of the energy output of that ancient feeding frenzy. By calculating its total radio emission, scientists can estimate just how much material the black hole consumed and how powerful its jets were during that violent chapter. Perhaps the most fascinating implication of this discovery is what it tells us about the current state of Andromeda's core. The presence of this fossilized lobe confirms that the central black hole is now in a long period of quiescence. It has effectively cleaned out its immediate vicinity, having consumed the fuel that powered its brilliant outburst. The galaxy has settled into a quieter, more stable state. This life cycle from violent activity to peaceful dormancy is a crucial part of how astronomers believe supermassive black holes and their host galaxies evolved together, a relationship known as co-evolution. The black hole's past activity may have even played a role in regulating star formation in Andromeda, as its powerful jets would have heated surrounding gas and blown it outwards, preventing it from cooling and collapsing into new stars. This single, faint radio ghost, therefore, is a palimpsest of galactic history, its fading signal writing a story of past fury, immense power, and the long, quiet peace that follows a cosmic storm. Tucked away in the sparse stellar population of the halo, astronomers have identified a star that burns with a deep, ruby-red light, a telltale signature of its bizarre and exotic nature. This is Object 12, a carbon star, and its very presence in this ancient environment is a profound anomaly. While carbon stars are not unheard of in the bustling, gas-rich disks of galaxies where stars are continually being born and dying, finding one in the halo is like discovering a single, freshly bloomed rose in the middle of a prehistoric fossil bed. It simply doesn't belong with the immensely old, metal-poor population that dominates this region, and its existence points to a very specific and dramatic life story. The defining characteristic of this star is its atmosphere, which is overwhelmingly rich in carbon. This peculiar chemistry is the result of a delicate and short-lived phase in the life of a mid-sized star. As such a star nears the end of its life, it swells into a red giant. In its churning depths, nuclear fusion creates helium, and then eventually, helium atoms fuse to create carbon. Through a powerful process called dredge-up, these newly forged carbon atoms are carried by convection currents from the star's core up to its surface. For a brief window of time, the star's outer layers contain more carbon than oxygen. This chemical imbalance causes carbon atoms to link together into soot-like particles right there in the star's atmosphere, filtering out the blue light and causing the star to glow with an intense, characteristic red hue. This carbon-rich shroud is the star's final, beautiful act of self-expression before its demise. But how did such a star, which clearly went through a complex chemical evolution, end up in the ancient halo? The leading theory is that it was not born in the halo at all. It likely formed much later in the history of the universe within a dwarf satellite galaxy orbiting Andromeda. This smaller galaxy would have contained the reservoirs of gas necessary for multiple generations of stars, allowing for the birth of this intermediate mass star long after the first primordial stars had died out. Billions of years later, as its host dwarf galaxy was gravitationally shredded and absorbed by Andromeda, this carbon star was stripped away and left to orbit in the halo as a solitary relic of its former home. Its presence is a chemical tag, a piece of evidence confirming that Andromeda's growth through galactic cannibalism included systems that were still actively forming stars relatively recently. This star is living on borrowed time. The carbon star phase is incredibly brief on cosmic scales, lasting only a few 100,000 years. Soon, it will expel its entire carbon-rich atmosphere into space in a final, gentle outburst, forming a beautiful planetary nebula. The carbon soot created in its atmosphere will be scattered into the interstellar medium, destined to one day be incorporated into new planets and perhaps even life forms in some distant future solar system. For now, however, its brilliant and predictable glow serves a critical purpose for astronomers. It is a standard candle, because we understand the intrinsic brightness of carbon stars in this specific phase. We can accurately measure how much their light has dimmed by the time it reaches us. This dimming directly tells us the distance to the star with remarkable precision. By pinpointing the location of this and other carbon stars in Andromeda's halo, scientists can triangulate the galaxy's distance from us more accurately than almost any other method, helping to calibrate the entire cosmic distance ladder that we use to measure the scale of the universe. This dying red giant, a temporary anomaly in the halo, thus becomes a fundamental yardstick, its faint light helping us map the vast expanses of the cosmos. Now, let's turn our attention to a phenomenon that isn't just hidden in darkness or faint light, but in the very fabric of spacetime itself. This is Object 13, a colossal binary black hole system thought to be contributing to the faint, perpetual hum of gravitational waves that rhythmically stretch and compress our entire universe. It's an object we cannot see or hear in any traditional sense, yet its presence is inferred by the delicate, synchronized dance of dead stars millions of light-years away. This system is believed to consist of two supermassive black holes locked in a tight, decaying orbital embrace, each with a mass millions of times greater than our Sun. They are the remnants of two galaxies that merged long ago, their central black holes eventually finding each other in the chaotic aftermath and settling into a mutual orbit. The key to their role as a gravitational wave contributor lies in their mass and their proximity. Their immense gravity creates profound distortions in spacetime, and as they orbit each other at a significant fraction of the speed of light, these distortions are whipped into a storm of propagating ripples, gravitational waves that radiate out across the cosmos, carrying energy away from the system. This steady loss of energy has a direct and measurable effect. It causes the orbits of the two black holes to slowly but inexorably decay. They are spiraling inward, destined to collide in a cataclysm that will shake the universe. But that final merger is likely millions of years in the future. For now, they are in a stable, long-lasting in-spiral phase, and it is this prolonged, rhythmic churning of space-time that makes them a perfect contributor to the gravitational wave background. It's not a single crash, but a continuous, low-frequency drone produced by their endless orbital motion. The evidence for this object's existence doesn't come from a telescope, but from a celestial timing network. Astronomers use pulsars, rapidly spinning neutron stars that emit beams of radio waves with the precise regularity of cosmic metronomes, as a galaxy-scale detector. By meticulously monitoring the arrival times of these pulses from an array of pulsars across the Milky Way for years, scientists look for correlated distortions. A passing gravitational wave will slightly alter the distance between Earth and a pulsar, minutely speeding up or slowing down the pulse's arrival time. The specific pattern of these timing anomalies across the sky can point back to loud sources in specific regions, and one such source appears to be located within Andromeda's halo, suggesting the presence of this incredibly massive, close binary system. This puts Object 13 into a fascinating cosmic context. It is not alone, it is one voice in a massive cosmic choir. Across the universe, countless other supermassive black hole binaries are in similar states of in-spiral, each generating their own gravitational wave signature. The combined effect of all these signals overlapping creates a stochastic background, a faint hum that permeates all of space. Detecting this background was a monumental achievement in astrophysics, and identifying individual contributors like this system in Andromeda helps us understand the population of these binaries as a whole, giving us insight into the merger history of galaxies across cosmic time. Our journey now takes us to a star that shouldn't exist, at least not according to our established textbooks on stellar evolution. This is Object 14, a solitary red giant star burning in the halo. To the untrained eye, it appears utterly normal, a large, aging star, cooling and expanding as it nears the end of its life. But when astronomers analyzed its spectrum, they found a chemical signature so bizarre and unexpected that it forces us to reconsider what we know about the inner workings of stars. This star contains an enormous, baffling abundance of the element lithium, a presence that defies every standard model of how stars create and destroy elements. Lithium holds a special and fragile place in cosmic chemistry. It was one of the only three elements forged in the primordial fire of the Big Bang, alongside hydrogen and helium. But unlike its robust companions, lithium is incredibly delicate. Inside the hot interiors of stars, lithium nuclei are fragile. They are easily destroyed, torn apart at temperatures above 2.5 million Kelvin, which is a temperature that exists just below the surface of most stars. Standard stellar physics dictates that as a star evolves, any lithium it was born with should be gradually depleted throughout its long life. By the time a sun-like star swells into a red giant, its lithium should be entirely gone, burned away billions of years earlier. Finding a red giant with high levels of lithium is like finding a perfectly preserved ice cube in the middle of a blast furnace. It simply shouldn't be possible. This presents a monumental mystery for the science of nucleosynthesis, which is the process by which stars create new elements. We understand the pathways that build heavier elements like carbon or oxygen through nuclear fusion. But we have no clear, established mechanism for a star to create significant new lithium in its interior, especially since that same interior is hot enough to immediately destroy it. The presence of so much lithium in this red giant suggests there is a gaping hole in our knowledge, a missing chapter in the stellar life cycle where some unknown, transient event can manufacture this fragile element and somehow bring it to the star's surface without it being annihilated. Astronomers have proposed several fascinating theories to solve this lithium puzzle. One leading idea involves a profound internal upheaval. As a star transitions into its red giant phase, its internal structure undergoes a dramatic reorganization. The convective zone, the outer layer where material churns like a boiling pot of water, suddenly plunges deep down into the star's interior. It's possible that this dredge-up could somehow tap into a region where a specific nuclear reaction, involving the fusion of helium with another element, is briefly producing beryllium. This beryllium, itself unstable, could then decay into lithium right there in the cooler outer layers, safely away from the destructive core. This would be a case of the star's own death, through accidentally synthesizing a new element it was always meant to destroy. Another compelling theory points to an external catalyst. Perhaps this star wasn't always alone. If it had a lower mass stellar companion, a small star like our Sun, that companion could have eventually evolved and swelled into a red giant itself, transferring material onto the star we see now. This donated material could have been enriched with lithium, either from the companion's own surface or from planets it may have consumed. Or the star might have recently engulfed a giant planet or a brown dwarf. These substellar objects can hold onto their primordial lithium, which was preserved in their cooler interiors. Swallowing such a massive object would inject a huge amount of fresh lithium directly into the star's outer atmosphere, creating the abnormal abundance we detect. The implications of this single, strange star ripple outward, touching on our understanding of the entire universe. Lithium is a key element for cosmologists. By measuring the amount of lithium in the oldest stars, they can test their models of the Big Bang itself. The fact that we see some ancient stars with very little lithium, and now others like this one with an overabundance, tells us that the story of this element is far more complex than we imagined. Its cosmic history isn't just about primordial creation and steady destruction. It must also include episodes of later production and redistribution, processes we are only just beginning to uncover. This lithium-rich giant, a chemical rebel in the quiet halo, is therefore a crucial clue, forcing us to rewrite the rules of stellar alchemy and acknowledge that even in their final acts, stars are still capable of profound surprises. Now we shift our focus from solitary wanderers to spectacular cosmic duos, pairs of stars locked in a gravitational embrace so intimate it leads to some of the most violent and energetic phenomena in the universe. In the sparse expanse of Andromeda's halo, astronomers have catalogued two such binary systems, each a powerhouse of high-energy physics and a testament to the dramatic consequences of stellar partnership. These are not gentle dances, they are tempestuous relationships where one star relentlessly feeds on the other, unleashing brilliant outbursts and powerful jets that can be seen clear across the intergalactic void. The first of these, Object 15, is known as a cataclysmic variable system. It consists of two stars, a main sequence star not unlike our Sun, and a white dwarf, which is the incredibly dense, Earth-sized core of a star that has already died. They orbit each other so closely that their gravitational interplay creates a devastatingly efficient transfer of matter. The white dwarf's powerful gravity strips material, primarily hydrogen, from the outer atmosphere of its larger companion. This stolen gas doesn't fall directly onto the white dwarf. Instead, it forms a swirling, flat disk of superheated plasma called an accretion disk, which orbits the dense primary star at fantastic speeds. Friction within this disk heats the gas to millions of degrees, causing it to glow intensely across the electromagnetic spectrum, from ultraviolet to X-rays. For most of its life, this system smolders at a relatively steady, high temperature, but periodically it erupts in a spectacular event known as a dwarf nova outburst. This occurs due to an instability in the accretion disk itself. As hydrogen continuously piles up in the outer regions of the disk, it eventually reaches a critical density and temperature. This triggers a sudden and dramatic change in the viscosity of the gas, causing it to rapidly heat up and spiral inward in a torrential cascade onto the surface of the white dwarf. In a matter of hours, the entire system can brighten by a factor of 100, shining with the fury of tens of thousands of suns before gradually fading back to its normal state over days or weeks. Observing these predictable eruptions in the halo provides astronomers with a natural laboratory to study the physics of accretion, a fundamental process that powers everything from forming planets to the most massive black holes in the universe. Our second binary system, Object 16, operates on an even more extreme level of violence. This is a microquasar, a name that reveals its awe-inspiring nature. If a cataclysmic variable is a tempest, a microquasar is a hurricane. This system also contains two stars, but here the primary is not a white dwarf. It is a stellar mass black hole or a neutron star, and its companion is a massive luminous star. The same process of accretion occurs, but the gravitational pull of a black hole is infinitely more voracious. The accretion disk here is far hotter, denser, and more energetic. The most staggering feature of a microquasar, and the reason for its name, is its ability to generate relativistic jets. As matter spirals inward at Chinese letter light speeds, immense magnetic fields and intense friction within the inner accretion disk accelerate some of the material away from the poles of the black hole or neutron star. These are not gentle flows, they are focused beams of ionized plasma shot out into space at over 90% of the speed of light. These jets punch through the interstellar medium of the halo, creating lobes of radio emission where they eventually collide with the tenuous gas that exists there. This entire structure is a perfect scaled-down replica of the jets and lobes seen emanating from supermassive black holes at the centers of active galaxies, or quasars, hence the term microquasar. The energy output of this system is staggering. The accretion process and the jets produce a constant torrent of high-energy radiation, from powerful X-rays to gamma rays. For astronomers, finding such a system in the halo is like discovering a miniature and accessible version of a galactic nucleus, allowing them to study the complex physics of jet formation and particle acceleration on human timescales rather than the million-year cycles of supermassive black holes. The presence of these two interacting binaries so far from Andromeda's star-forming disk is itself a clue to their history. They were likely born in a dense cluster or a small galaxy that was torn apart, and their tight gravitational bond kept them together as they were flung into the halo, where they continue their dramatic and luminous dance, utterly isolated yet shining as beacons of some of the most energetic processes the universe has to offer. But woven through this menagerie of stellar corpses and cosmic engines is something far more subtle, and in its own way far more ancient. This is Object 17, a wispy, ethereal filament of gas that represents a direct, unaltered portal to the universe's very first moments. Unlike the metal-rich planetary nebula or the star-forming cloud, this structure is composed of pristine hydrogen and helium, a relic of primordial gas that has miraculously never been touched by the life and death of stars. It is a cosmic fossil, but not of a star or a galaxy. It is a fossil of the raw material from which everything else was eventually made. The existence of such a pure structure is a minor miracle in a universe that has been continuously polluted for over 13 billion years. After the Big Bang, the cosmos was a hot, dense soup of hydrogen, helium, and a trace amount of lithium. As the first stars ignited, their nuclear furnaces began forging heavier elements like carbon, oxygen, and iron. When these massive first stars died in spectacular supernova, they seeded their surroundings with these newly created metals, enriching every subsequent generation of stars and galaxies. This process is so efficient that finding a cloud of gas that has completely avoided this pollution is incredibly rare. This filament is a time capsule, a pocket of the universe that has remained in its original pure state, never collapsing to form stars and thus never contributing to the cosmic cycle of creation and destruction. Detecting something so elemental and faint requires ingenious methods. Astronomers cannot see this gas in visible light. Instead, they rely on a cosmic background source, the light from an even more distant quasar. As this brilliant beacon's light travels across the universe on its way to our telescopes, it passes through the filament. The pristine hydrogen within the cloud absorbs specific, very precise wavelengths of this light. Because the gas has no heavier elements to complicate the spectrum, the absorption lines it creates are exquisitely sharp and clear, a pure signature of hydrogen that is unmistakable against the quasar's broad emission. It is like finding a single, perfectly clear raindrop in a muddy puddle. Its purity makes it stand out brilliantly to those who know how to look. Studying this object is like opening a window to a time before the first starlight ever graced the cosmos. Its chemical simplicity allows scientists to test our fundamental models of the Big Bang itself. The precise ratio of hydrogen to helium and the minute amount of lithium in this filament must perfectly match the predictions of nucleosynthesis models for the early universe. Any deviation would force a radical rethink of our understanding of physics in the first few minutes of existence. Furthermore, the very structure of the filament, its density, temperature, and distribution provides a unique glimpse into the conditions of the cosmic web before galaxies ever began to form. It is a snapshot of the universe in its infancy, a simple, quiet place of potential, waiting for gravity to begin its slow, patient work of building the complexity we see today. Yet another mystery carves its path through the halo's darkness, not as a glowing cloud or a faint star, but as a profound and unsettling absence. The evidence for this object, a runaway supermassive black hole, is not what we see but what we don't see, and the gravitational chaos it left in its passing. Imagine a cosmic wrecking ball, an object weighing millions of suns, not peacefully orbiting the galactic center where it belongs, but hurtling through the halo's outskirts at incredible speed, a monarch dethroned and cast into exile. The very concept sounds like science fiction, but the physics behind such a dramatic ejection are terrifyingly real. It begins with a galactic merger, an event we know has shaped Andromeda's history. When two galaxies collide, their central supermassive black holes eventually sink to the new common center through a process called dynamical friction. There they form a binary pair orbiting each other in a tightening dance. As they spiral closer, they radiate energy away in the form of gravitational waves. But if a third, sizable black hole from another merged galaxy is introduced into this chaotic mix, the three-body gravitational interaction can become violently unstable. In a flash of cosmic chaos, the least massive of the three can be slingshotted away at phenomenal speed, catapulted clear out of the galactic core and into the vast halo, or even into intergalactic space forever. So how do you find an invisible object that emits no light, especially one that is moving so fast? You look for the wreckage it leaves behind. Astronomers searching through the halo have identified a strange, linear stream of stars that is far more perturbed and chaotic than the graceful tidal tails we see from disrupted dwarf galaxies. This stream appears to have been recently and violently stirred, its stars buzzing with unusual kinetic energy. The leading explanation is that a tremendously massive, compact object recently plowed through it. The gravitational wake from this intruder would have acted like a speedboat racing through a calm lake, leaving a distinct V-shaped pattern of disturbed stars in its path, a telltale sign of a recent and massive gravitational encounter. The properties of this stellar wake are the key to identifying the culprit. By meticulously mapping the motions of these perturbed stars, scientists can run the gravitational tape backwards. They can calculate the mass required to cause such a disruption and trace the likely path the object took. The estimated mass for this invisible intruder is staggering, falling squarely in the range of a supermassive black hole. Its projected path is the most damning evidence of all, tracing a straight line directly away from the galactic center, exactly what you would expect from an object violently ejected from the core. This isn't just a wandering intermediate black hole. This is a behemoth that was once the heart of a galaxy itself, now doomed to wander the darkness alone, a king without a kingdom. The implications of such a discovery are profound. This runaway black hole would be dragging its own retinue along with it, a tightly bound cluster of stars that were once close to it in the core and were pulled along by its gravity. It might even be surrounded by a faint shroud of gas and dust, glowing faintly as it is heated by periodic accretion events. But most importantly, its existence provides the ultimate proof of a specific and dramatic past event. It is the smoking gun for a triple black hole interaction, confirming that Andromeda's merger history involved not just one, but multiple sizable galaxies, each with its own central supermassive black hole. This cosmic fugitive, racing silently through the void, is therefore one of the most compelling pieces of evidence we have for the violent, chaotic, and hierarchical way in which our galactic neighbor was built. While our journey has revealed objects both dark and brilliant, our next discovery challenges the very definition of what a galaxy can be. This is Object 19, an entire star system that is virtually invisible to optical telescopes, a ghost in plain sight. Yet, when viewed through the infrared eyes of space observatories, it blazes with the intensity of a trillion suns. This dramatic difference between its visible and infrared brightness has earned it a specific classification, an extremely dusty, infrared bright but optically faint galaxy. It is a hidden factory of stars operating behind a nearly impenetrable curtain of cosmic soot, revealing a crucial but often overlooked phase of galactic life. The reason for its strange appearance lies in its phenomenal dust content. This isn't the gentle, diffuse dust we see as dark veins in the Milky Way. This is a thick, choking pall of carbon and silicate grains that envelops the entire galaxy. This dust did not appear from nowhere. It is the direct product of a ferocious cycle of star birth and star death. Massive stars live fast and die young, and in their spectacular supernova deaths, they blast out the heavy elements forged in their cores. These elements condense into tiny solid particles, dust, which are then swept up by stellar winds and radiation pressure, filling the interstellar medium with a dense, opaque fog. In this galaxy, that process has run amok, creating an environment so dusty that it completely blocks the visible light produced within. So why does it shine so brightly in the infrared? The answer is a simple principle of physics. Energy cannot be created or destroyed, only transformed. The visible light from the galaxy's countless newborn stars is not lost, it is absorbed by those countless trillions of dust grains. The dust, having consumed that energetic starlight, heats up, and just like any warm object, it re-radiates that energy, but at a much longer wavelength in the infrared part of the spectrum. The more intense the starlight is behind the dust, the hotter the dust becomes and the more brilliantly it glows in the infrared. This galaxy's incredible infrared luminosity is therefore a direct and precise measurement of the incredible firepower of the stellar factory hidden within. We are essentially seeing the waste heat from a monumental industrial operation. This hidden activity is a starburst on a colossal scale. Astronomers estimate that stars are being born here at a rate hundreds, perhaps even thousands of times faster than in our own Milky Way. This isn't normal star formation, it is a galaxy-wide frenzy, a firestorm of creation that is rapidly consuming its vast reservoirs of gas. Such intense periods of star formation cannot last long. They are cosmic blazes that burn through their fuel in a relative flash, perhaps only 100 million years. This tells us we are witnessing a brief, explosive, and critically important chapter in a galaxy's evolution. But how did such a violently active galaxy end up in Andromeda's halo? The prevailing theory is that it is not a native of the halo but a recent arrival. it was likely a gas-rich dwarf galaxy that strayed too close to Andromeda. The gravitational interaction with the giant galaxy, or perhaps a close encounter with another satellite, compressed its vast gas clouds, triggering the devastatingly efficient chain reaction of star formation we see today. It represents a hidden phase of evolution because without infrared telescopes, we would be completely blind to this entire class of objects. They would simply be missing from our maps of the universe, their profound contribution to the cosmic story of star formation entirely overlooked. This single, dusty enforcer is a powerful reminder that the universe is always more complex than it appears, and that to see its true face, we must learn to look in every possible light. Nestled within the vast stellar halo, one particular globular cluster initially appeared to be just another ancient and dense collection of stars, a familiar sight to astronomers. But as researchers trained their most powerful instruments on this object, designated Mayol 2, they noticed something deeply unusual about the motion of its stars. At the cluster's core, a tight-knit group of suns was whipping around at impossible velocities, orbiting an invisible focal point with a gravitational pull so fierce it could only mean one thing: a hidden, massive anchor was lurking at its heart. This was no ordinary cluster, it was a cosmic safe holding a profound secret, a missing link in our understanding of how the universe builds its most terrifying objects. The key to the discovery lay in the precise measurement of stellar velocities. Using the Hubble Space Telescope, astronomers spent years tracking the individual paths of stars near the cluster's center. In a typical globular cluster, the speeds of these stars follow a predictable pattern, gradually decreasing as you move outward from the core, governed by the combined gravity of all the visible stars. Here, however, the inner stars were moving so fast that their velocity alone indicated the presence of a dark, central mass equivalent to thousands of suns, all concentrated into a region smaller than our solar system. The math was unequivocal. The only object that could possibly contain so much mass in such a tiny volume is a black hole. But this was not the supermassive black hole found in galactic centers, nor was it the stellar mass black hole left behind by a single supernova. This was something entirely different, an intermediate mass black hole, a long-theorized but elusive class of object that had never been convincingly confirmed until now. This discovery is so monumental because it appears to solve a major puzzle in astrophysics. How do supermassive black holes, which weigh millions or even billions of solar masses, get so big? We know that stellar mass black holes, which are up to a few dozen times the mass of our Sun, form from the collapse of massive stars, but there is a vast gulf between these and the behemoths at the centers of galaxies. The existence of an intermediate mass black hole, especially one residing in a globular cluster, provides a compelling potential pathway. It suggests that the early universe may have been seeded with these mid-sized black holes, which then acted as building blocks. Through eons of galactic mergers and collisions, these intermediate black holes could have merged with each other and accreted vast amounts of gas, gradually growing into the supermassive giants we observe today. This specific cluster, Mayol 2, might itself be the remnant core of a devoured dwarf galaxy, and its black hole could be the dormant engine that once powered a much smaller system, now captured and orbiting within Andromeda's halo. The methods used to find this object are a testament to modern astronomical detective work. Since the black hole itself is invisible, its presence had to be inferred indirectly through its gravitational influence. Astronomers didn't just measure star speeds, they constructed detailed dynamical models of the entire cluster. They calculated how every single star should be moving based on the gravity of all the others, and the model only matched the observed, frenzied motions when they included the gravitational pull of a central black hole weighing 20,000 solar masses. This object, therefore, is more than just a strange resident of the halo. It is a crucial piece of observational evidence that helps bridge the gap in black hole evolution, confirming a key prediction of astrophysical theory and providing a glimpse into the hierarchical growth of structures throughout the cosmos. Now our journey brings us to a cosmic paradox, a celestial act of creation born from utter destruction. This is Object 21, a dense knot of brilliant young stars and glowing gas that appears to be forming an entirely new galaxy. But this isn't a genesis from primordial matter, it's a rebirth from wreckage, a structure emerging from the debris of a violent collision. This object is a tidal dwarf galaxy candidate, and its very existence challenges our most fundamental definitions of what a galaxy actually is. Typically, galaxies are thought to form from the bottom up. Vast clouds of pristine hydrogen and helium from the Big Bang slowly coalesce under gravity, eventually igniting their first stars and growing over billions of years through mergers. A tidal dwarf galaxy turns this story on its head. It forms from the top down, born from material that has already been processed by a previous generation of stars. Its origin lies in the chaotic aftermath of a galactic collision. When two large galaxies gravitationally tear at each other, their immense tidal forces can pull colossal streams of gas, dust, and even stars out into the halo. Within these drawn-out tidal tails, the densest regions of gas can collapse under their own gravity, sparking intense bursts of new star formation. If enough material gathers in one of these knots, it can become gravitationally bound, forming a new, independent entity, a galaxy born from the ruins of its parents. The evidence for this object's unique origin is written in its starlight. Spectroscopic analysis reveals a critical clue. Its stars are surprisingly metal-rich. Remember, metals in astronomy mean any element heavier than hydrogen and helium. This high metal content tells us the gas that formed these stars was not pristine, it was pre-polluted. It was gas that had already been cycled through previous generations of stars inside the larger galaxies that collided, enriched with carbon, oxygen, iron, and all the other elements forged in stellar cores and scattered by supernova. This is the crucial distinction. This candidate isn't made from the raw material of the early universe, it's made from the recycled remains of a galactic disaster. This presents a fascinating challenge to the traditional definition of a galaxy. One of the key criteria has always been that a true galaxy must be dominated by dark matter, the mysterious substance that makes up the vast majority of mass in the universe and provides the gravitational scaffolding for primordial galaxy formation. But a tidal dwarf galaxy likely contains very little, if any, dark matter. It was formed from disk material ripped out of its parent galaxies, and the disks of spiral galaxies are composed primarily of ordinary baryonic matter, stars, gas, and dust. The dark matter resides in the large, spherical halo that surrounds the disk. Therefore, this new object would be an island of stars and gas held together almost exclusively by its own visible mass, a concept that upends the standard model of what constitutes a galactic structure. Witnessing the potential birth of such an object gives astronomers a front-row seat to a dynamic and ongoing process. It shows that galaxy formation isn't just an ancient event locked in the distant past, it's a continuing narrative. The very presence of this young, vibrant object in Andromeda's halo is direct evidence of a relatively recent and dramatic merger, a cosmic event that was violent enough to scatter the building blocks of a new generation into the darkness. This tidal dwarf candidate is more than just a collection of stars. It is a living testament to the cyclical nature of the cosmos, where destruction and creation are two sides of the same coin, and where even in the aftermath of chaos, new islands of light can emerge. Drifting through the silent expanse of the halo, we find a star in the midst of a profound and beautiful transformation, one that leaves a visible mark on the void behind it. This is Object 22, a mirror variable star, a pulsating red giant that is not merely shining but is actively dying, shedding its own atmosphere into space and creating a spectacular comet-like tail that stretches across light years. This cosmic lighthouse, with its rhythmic dimming and brightening, is performing a final, elegant dance, and its motion through the halo's near-perfect vacuum is allowing us to witness the process of stellar death in breathtaking detail. The heart of this phenomenon is the star's inherent instability. A mirror variable is a sun-like star in its final act, having exhausted the hydrogen fuel in its core and swelled into a colossal, cool red giant. In this bloated state, its outer layers become loosely bound and begin to rhythmically pulsate, expanding and contracting over a regular period that can last hundreds of days. With each pulsation, the star's atmosphere becomes so distended that its gravity can no longer hold onto it. Enormous amounts of material, dust, gas, and complex molecules are gently but persistently pushed away by the pressure of its own starlight, creating a continuous, dense stellar wind that flows out into the surrounding space. This alone is a common fate for aging stars. What makes this particular object so extraordinary is its rapid motion and its environment. This mirror variable is not sitting still. It is racing through the halo at a considerable speed. The halo is not completely empty. It contains a sparse, diffuse medium of individual gas atoms and tiny dust grains. As the star plows through this tenuous material, its own ejected wind collides with it. Think of it like a speedboat moving through a calm lake. The boat creates a wake behind it. In this case, the boat is the star and its powerful wind, and the water is the halo's interstellar medium. The interaction between the two creates a bow shock ahead of the star and, crucially, a long, streamlined tail of concentrated dust behind it, which is cooled and condensed by this collision process. This tail, or wake, is what makes the star visible to our telescopes in a whole new way. The dust grains in the wake are excellent at reflecting the star's own light and radiating in the infrared. This allows us to actually see the structure, a brilliant trail of cosmic soot that marks the star's path through the galaxy's outskirts. By studying the length, shape, and density of this tail, astronomers can become celestial historians. They can calculate how long the star has been in this intense mass loss phase, estimate the total amount of material it has shed, and even trace its trajectory backwards to understand where in the galaxy it was originally born before being flung out into the halo. The composition of this dusty wake is a treasure trove of information about the inner workings of stars. The material being shed is rich with elements like carbon, oxygen, and silicon. As it expands and cools away from the star, these elements condense to form solid particles, specks of graphite, silicates, and even more complex compounds. This is the primary way that the universe disperses the heavy elements forged in stellar cores, seeding the interstellar medium with the raw materials for new planets and, ultimately, life. This single star, with its brilliant tail, is a miniature factory for stardust, giving us a front-row seat to one of the most crucial recycling processes in the cosmos. Its solitary journey illustrates a fundamental truth, that even in death, a star contributes to the future, its final breaths building the foundations for worlds yet to be born. Now we turn our gaze to a structure that is not a single object, but a vast and dynamic river system flowing through the cosmic watershed of intergalactic space. Designated as Object 23, this is a high-velocity cloud complex, a congregation of numerous massive clouds composed primarily of neutral hydrogen gas. These are not the quiet, settled reservoirs of gas within a galaxy's disk. These are interlopers, fresh material falling into the Andromeda system for the very first time, representing the ongoing, real-time build-up of the galaxy from the raw materials of the cosmic web. The discovery of these clouds is a feat of radio astronomy, as they are completely invisible to optical telescopes. Hydrogen, the most basic element, emits a faint but specific radio signal at a wavelength of 21 centimeters when the spins of its single proton and electron flip and align. By tuning their massive radio dishes to this frequency, astronomers can map the distribution of this primordial gas even when it is too cold and diffused to glow on its own. What they found surrounding Andromeda was not a uniform haze, but a complex architecture of distinct clouds, filaments, and streams, many of them moving at velocities that are radically different from the orderly rotation of the galaxy itself. Their high speed is the first clue that they are newcomers, not yet settled into the galaxy's gravitational sway. The origin of this infalling material is a subject of intense study with two compelling possibilities. The first is that these clouds are truly primordial, vestiges of the cosmic web itself. After the Big Bang, the universe was not perfectly smooth. Matter clumped into a vast, web-like structure of filaments and voids. This high-velocity complex could be a tendril of that ancient web, a filament of gas that has spent billions of years slowly condensing under its own gravity, only now finally being drawn into the deeper gravitational well of the Andromeda galaxy. The second possibility is that this is recycled material, gas that was once blasted out of Andromeda or one of its satellite galaxies by a powerful past event, like a period of intense supernova explosions or an outburst from the central black hole. This ejected material is now completing a vast cosmic loop, falling back home in a process called a galactic fountain. Regardless of their origin, the fate of these clouds is a spectacular demonstration of galactic ecology. As they plunge into the halo and eventually encounter the gaseous disk of Andromeda, they will not merge gently. They will collide with the existing interstellar medium at supersonic speeds, creating immense shock waves that ripple through the galaxy's gas. These shock fronts are the ultimate trigger for star formation. They compress vast, cool regions of gas to the critical densities needed for gravity to take over and collapse them into new stellar nurseries. This ongoing accretion is the primary way a galaxy like Andromeda, which has largely consumed its original gas supply, continues to fuel new generations of stars. It is a delivery of groceries to the cosmic pantry, ensuring the galaxy does not stagnate. The presence and behavior of this high-velocity complex provide a critical link between theory and observation. Cosmological simulations of the universe predict that large galaxies should still be accreting fresh gas from their surroundings in exactly this filamentary manner. For a long time, this was a prediction that was difficult to confirm observationally. The discovery and detailed mapping of Object 23 and structures like it provide the direct, tangible evidence that this process is not just a theoretical idea, but is actively happening right next door. We are witnessing in real time the hierarchical growth of a galaxy, a slow and majestic rain of primordial matter that has been falling for billions of years and will continue to shape Andromeda's future for billions more. Lurking in the quiet darkness of the halo is a signature of pure, unadulterated energy, a beacon that shouts its presence across the electromagnetic spectrum yet refuses to reveal its identity. This is Object 24, an unidentified X-ray source or UX. It appears in the data from orbiting X-ray observatories as a brilliant, point-like pinprick of high-energy radiation, a signal so intense it demands attention. Yet, when astronomers swing every other instrument they have toward its coordinates, optical telescopes to see it, infrared scopes to feel its heat, radio dishes to hear its whisper, they find absolutely nothing. It is a cosmic contradiction, a raging fire visible only by the shadow it casts in a single, specific light, a puzzle that has spawned a fascinating list of potential explanations, each more exotic than the last. The most conservative, yet still thrilling, theory points to a quiescent stellar mass black hole. Imagine a black hole, the remnant of a massive star that is currently in a state of peaceful solitude. It is not actively feeding from a companion star. No torrent of gas is spiraling into its event horizon to create a glowing accretion disk. It sits alone, dark and invisible. But even in this quiet state, the immense gravitational pull of the black hole can still exert its influence. If a single, dense molecular cloud or a lone, wandering planet were to drift too close, the black hole's gravity could violently compress and heat that material just by pulling on it, causing it to glow fiercely in X-rays for a relatively brief period before the snack is consumed and darkness returns. This would create a temporary, brilliant X-ray flash with no other visible counterpart, a single gulp in the void that leaves no lasting trace. A second compelling candidate is a neutron star exhibiting extreme behavior. We know neutron stars can be incredible powerhouses, and one type in particular fits this mysterious profile, a magnetar. A magnetar is a neutron star born with a magnetic field of almost unimaginable strength, a quadrillion times more powerful than Earth. These fields are so intense they can literally twist the star's solid crust, causing starquakes that release colossal bursts of gamma rays and X-rays. A magnetar in a quiet phase, not actively pulsing as a radio pulsar, could produce such a sudden, brilliant X-ray outburst from a crustal fracture that it would dominate the view for a short time, appearing as a singular point source with no other observable emission, its incredible distance in the halo rendering its visible light counterpart too faint to detect. Then we must consider the possibility of something entirely new, a class of object not yet catalogued in our astronomy textbooks. Could this be evidence of a quark star? This is a theoretical stellar remnant that is even denser than a neutron star. The idea proposes that under such immense gravitational pressure, the neutrons themselves break down into their constituent parts, quarks. This would create a soup of free quarks, an exotic state of matter that could produce a very specific and intense X-ray signature unlike anything we've seen before. Or perhaps it is a binary system so unusual it defies our current models, like two white dwarfs on the verge of colliding, creating a runaway nuclear reaction on their surfaces that flashes in X-rays before they merge. Each exotic explanation pushes the boundaries of known physics, reminding us that for every answer we find, the universe is always ready to present a new, more baffling question. This single, unresolved point of energy is a humbling reminder that our maps of the cosmos are still filled with blank spaces, marked only by the words, "Here be dragons." Shifting our perspective to the radio spectrum reveals a structure of breathtaking symmetry and power, one that tells a story of intermittent cosmic fury. Catalogued as Object 25, this phenomenon appears not as a collection of stars, but as a brilliant and perfectly paired set of radio lobes. These colossal, bubble-like structures hang in space on opposite sides of an invisible central point, glowing intensely with the synchrotron radiation emitted by electrons spiraling at near light speed within powerful magnetic fields. This classic double-lobed structure is the unmistakable signature of a past eruption from an active galactic nucleus, a phase where a supermassive black hole feasted on matter and launched jets of plasma that eventually billowed out into these massive radio-emitting clouds. The sheer scale of these lobes, stretching across tens of thousands of light-years, speaks to the immense energy of that ancient event, an outburst that likely lasted for millions of years before the central engine finally fell silent. Yet the story becomes infinitely more compelling when we train optical telescopes on the precise center of this radio structure. There we find Object 26, a faint, peculiar, and decidedly disturbed-looking galaxy. It is not the grand spiral or smooth ellipse we might expect to anchor such a powerful radio source. Instead, it appears messy and asymmetric, with faint tidal tails and an irregular structure that immediately suggests a violent history. This is the optical counterpart, the host of the double radio source, and its battered appearance is the first major clue that we are witnessing a galaxy that has recently undergone a dramatic transformation, likely a merger with a smaller companion. The most fascinating aspect of this pair is the potential link between the galaxy's chaotic state and the radio lobes that surround it. Astronomers have a compelling theory that this system represents a prime example of a restarting radio galaxy. The sequence of events likely began billions of years ago when this galaxy, then a normal system, experienced its first period of activity. Its central black hole was active, consuming gas and producing the first set of jets that created the enormous, but now fading, outer radio lobes we see today. That phase eventually ended as the black hole consumed the available fuel in its immediate vicinity, and the galaxy entered a long period of quiescence. The recent merger, evident in the galaxy's disturbed appearance, is the key to the second act. The gravitational turmoil of the collision funneled vast new reservoirs of cold gas and stars directly toward the dormant central black hole. This sudden delivery of fresh fuel reignited the engine, waking the black hole from its slumber and initiating a new, younger phase of jet activity. We may now be witnessing the very beginning of this new outburst, where freshly launched jets are just starting to inflate new, smaller lobes of radio emission inside the older, larger ones left over from the first eruption. This creates a unique nested structure, a cosmic Russian doll of galactic activity, with the evidence of two distinct eras of outbursts visible at once. This paired observation provides an unparalleled window into the life cycle of supermassive black holes and their intimate connection with their host galaxies. It demonstrates that a black hole's active phase is not necessarily a single continuous event, but can occur in distinct episodes, each separated by eons of silence and each triggered by a new influx of material, often delivered by a galactic collision or merger. The faint, disturbed galaxy is not just a host, it is the trigger, its own dramatic evolution directly governing the behavior of the monstrous engine at its heart. This entire system stands as a stunning illustration of feedback and renewal on a galactic scale, where destruction gives birth to creation, and a quiet giant can be awakened to once again shape the space around it with unimaginable power. In the vast and varied population of Andromeda's halo, one star stands apart not for its size or its speed, but for its profound and ancient purity. This is Object 27, a stellar time capsule so pristine that its composition offers a direct, unaltered window into the conditions of the universe mere millions of years after the Big Bang. It is what astronomers call an extremely metal-poor star, but that term barely captures its significance. This is not merely a star with few heavy elements. It is a fossil, a surviving relic from the very first generation of stars that ever illuminated the cosmos, and its light carries the chemical signature of a universe before planets, before galaxies, and before life as we know it. The story of this star begins with the very first moments of everything. In the primordial universe, after the initial expansion and cooling, the only elements in existence were hydrogen, helium, and a trace amount of lithium, forged in the nuclear furnace of the Big Bang itself. There was no carbon, no oxygen, no iron, none of the fundamental building blocks of planets or life. The first stars, known as population 3 stars, formed from this pristine gas. They were behemoths hundreds of times more massive than our Sun, and they lived ferociously short lives, burning through their fuel in only a few million years before ending their existence in cataclysmic supernova. It was in these first, violent deaths that the universe was seeded with the first heavy elements, the astronomical metals that would pollute all future generations of stars. Object 27 is a second-generation star, one of the very first to form from the ashes of those initial pioneers. Its spectrum, the unique fingerprint of light that reveals its chemical composition, is astonishingly simple. The lines for hydrogen and helium are dominant and clear, but the telltale lines that signify heavier elements like iron, carbon, and oxygen are almost completely absent. When astronomers calculated its metallicity, the fraction of its mass that is made up of elements heavier than helium, the number was so low as to be nearly immeasurable, placing it among the most metal-poor stars ever identified. This profound lack of pollution means it formed from a cloud of gas that was enriched by only one, or at most a few, of those first supernovae. It is a snapshot of the universe's chemical state before widespread nucleosynthesis could begin in earnest. Studying the specific pattern of the few elements it does contain is like reading a forensic report on the supernova that gave it birth. The relative amounts of certain elements, like carbon compared to iron, can tell us about the mass and explosion mechanism of that very first star. Did it explode with full force, scattering all its newly forged elements? Or did it collapse directly into a black hole, retaining most of its heavy elements and only releasing a small, specific subset into the surrounding gas? The subtle clues hidden in the faint spectral lines of Object 27 help astronomers answer these questions, providing a window into the physics of the very first stellar deaths. This single point of light is therefore a living record, its chemistry encoding the life story of a star that died over 13 billion years ago. Its survival for so long is another stroke of cosmic fortune. To have endured from such an early epoch, it must be a very low-mass star. Massive stars burn brightly and die young, but smaller stars like red dwarfs can sip their hydrogen fuel slowly enough to shine for trillions of years. This star is a celestial miser, hoarding its energy and persisting through nearly the entire history of the universe, all the while preserving its pristine composition in its outer layers, virtually unchanged since its birth. Finding it in the halo makes perfect sense. This ancient region is the galactic equivalent of an archaeological dig site, where the oldest relics of the galaxy's formation have settled and been preserved, away from the churning, metal-rich environment of the galactic disk. The discovery of such a star is more than just a record-breaking entry in a catalogue. It is a crucial benchmark for our understanding of cosmic evolution. The predicted abundance of elements from Big Bang nucleosynthesis models can be tested against the actual measurements from this star, and so far, the match is remarkably good, confirming our theories about the universe's first few minutes. Furthermore, its existence provides a critical data point in the search for the elusive first-generation stars themselves. While we may never directly observe a population 3-star as they lived and died so quickly, we can study their children, stars like Object 27, to understand the nature of their legendary parents. This faint, ancient sun burning quietly in the halo is our most direct link to the dawn of time, a silent witness to the first moments of light breaking through the cosmic dark. Yet another echo of that past fury hangs in the halo, a structure so immense it defies easy comprehension, a pair of colossal bubbles that glow not in visible light, but in the most energetic radiation the universe can produce. This is Object 28, a vast gamma-ray bubble, one half of a symmetrical structure that balloons outward from Andromeda's core, extending tens of thousands of light-years into the halo above and below the galactic plane. To our eyes, this region is pure emptiness, but to instruments like the Fermi Gamma-Ray Space Telescope, it is a faint yet unmistakable glow of high-energy photons, a ghostly testament to a cataclysm of almost unimaginable power that rocked the galaxy in its distant past. The formation of such a structure is intimately tied to the beast at the galaxy's heart, its supermassive black hole. During an active phase, as vast quantities of matter spiral into the black hole's accretion disk, not all that material is consumed. A significant fraction of it is channeled and accelerated by powerful magnetic fields into two opposing, narrow jets of relativistic particles that scream outward at nearly the speed of light. These jets act like cosmic blowtorches, plowing into the much slower-moving material that surrounds the galaxy, the hot gas of the circumgalactic medium. The jets inject immense energy into this gas, heating it and pushing it outward, slowly inflating gigantic, balloon-like cavities on either side of the galactic center. These are the Fermi bubbles, and they are filled with a soup of ultra-high-energy particles and tangled magnetic fields. The faint gamma-ray glow we detect is the final clue in this cosmic detective story, revealing what is happening inside these bubbles long after the jets that created them have shut down. The bubbles are filled with cosmic rays, which are primarily protons accelerated to fantastic speeds. As these high-energy protons race through the bubble, they occasionally collide with the slower-moving protons of the ordinary, tenuous gas that is also trapped inside. This proton-proton collision creates a pion, an unstable subatomic particle that almost immediately decays into two gamma-ray photons. It is this cascade of particle physics, happening on a galactic scale, that produces the faint, diffuse haze of gamma rays that marks the entire volume of the bubble. We are essentially seeing the afterglow of a particle accelerator the size of a galaxy. The sheer size and energy of this structure allow astronomers to perform a remarkable calculation. They can effectively forensically reconstruct the power and duration of the black hole's ancient outburst. By measuring the total gamma-ray flux and the volume of the bubble, they can estimate the total energy that was required to inflate it. The numbers are staggering, pointing to an eruption that likely lasted for millions of years and released energy equivalent to the simultaneous explosion of millions of supernovae. This wasn't a brief flicker, it was a sustained galactic-scale hurricane of energy that fundamentally reshaped the environment around Andromeda, blowing huge amounts of gas out into the halo and likely shutting down star formation across large regions of the galaxy for eons. This discovery firmly places our own Milky Way into a broader cosmic context, as we have a very similar, though slightly smaller, pair of Fermi bubbles emanating from our own galactic center. Finding these structures in both major galaxies in our local group suggests that such energetic outbursts are not rare anomalies, but a standard part of the life cycle of a large spiral galaxy. These bubbles are a form of feedback, a way for the central black hole to regulate the growth of its host. By periodically blasting the surrounding gas with these tremendous outflows, the black hole prevents it from cooling and falling back in to form too many new stars, or from feeding the black hole itself too quickly. This giant, faint bubble is therefore more than just a fossil. It is a sign of a balancing act, a dramatic mechanism that helps shape galaxies into the stable, long-lived structures we observe today. Now we come to a phenomenon that transforms the halo itself into a cosmic observatory, a natural lens of unimaginable power. This is Object 29, an incredible optical illusion on a galactic scale where the gravitational pull of a massive object in Andromeda's halo has warped the fabric of spacetime itself, bending and magnifying the light from a far more distant galaxy that lies perfectly behind it. This effect, known as gravitational lensing, uses the halo's own invisible mass as a giant telescope, offering us an unprecedented and exquisitely detailed view of the early universe that would otherwise be forever beyond our sight. The principle behind this cosmic magnifying glass is one of Einstein's most famous predictions, that mass curves spacetime and light must follow that curvature. Imagine placing a heavy bowling ball in the center of a stretched rubber sheet. The sheet will dip. Now roll a marble past the bowling ball. Its path will curve inward following the dip. In the cosmos, the bowling ball is a massive object, in this case, a dense cluster of stars or a large concentration of dark matter within Andromeda's halo. The marble is not a particle of matter, but a beam of light from a galaxy billions of light years further away. As this distant light travels toward us, it passes through this curved region of spacetime created by the massive foreground object. The light doesn't travel in a straight line, its path is bent, and this bending can focus and amplify the light, much like a glass lens focuses light in a telescope. The result is that the faint, distant galaxy appears to us not as a single smudge, but as multiple, distorted, and brilliantly magnified images arranged in a perfect circle or arc around the foreground lens, a pattern known as an Einstein ring. This rare alignment provides astronomers with a powerful tool for cosmic exploration. The most immediate benefit is magnification. The lensing effect can amplify the light of the background galaxy by a factor of 10, 50, or even more. Suddenly, a galaxy so distant it would normally be a faint, unresolved speck even to the Hubble Space Telescope is brought into sharp focus. We can resolve its structure, distinguishing spiral arms, star-forming regions, and perhaps even clusters of bright young stars. This allows for a detailed study of galaxy morphology and stellar populations at a time when the universe was young, providing a direct comparison to the mature galaxies we see in our local neighborhood. Beyond simple magnification, the lensed image acts as a diagnostic tool for the lens itself. The exact shape, brightness, and number of the multiple images are exquisitely sensitive to the mass distribution of the foreground object that is causing the lensing. By meticulously modeling the distortions in the Einstein ring, scientists can perform a technique called gravitational lens modeling. This allows them to map the distribution of mass in the lensing object with incredible precision, regardless of whether that mass emits light. It is one of the most powerful and direct methods we have for detecting and weighing dark matter clumps within the halo, confirming their existence and measuring their shape and density profile purely through their gravitational influence. The distant galaxy itself becomes a probe for fundamental cosmology. Because its light has been traveling for so long, we are seeing it as it was billions of years ago. By measuring its redshift and comparing its detailed properties to models of galactic evolution, we can test our understanding of how galaxies form and change over cosmic time. Furthermore, if a supernova explodes in that distant galaxy, the lensing effect can create multiple images of the same explosion, appearing at different times due to the varied paths the light takes around the lens. Monitoring these time-delayed supernova images provides an independent way to measure cosmological distances and the expansion rate of the universe. This single, fortuitous alignment in Andromeda's halo, therefore, is far more than a curiosity. It is a unique natural laboratory that simultaneously reveals the hidden mass structure of our closest galactic neighbor and provides a crystal-clear window into the ancient, formative years of the cosmos. And now we reach the final and perhaps most profound mystery in our tour of Andromeda's halo, an object that represents the ultimate challenge to our perception of the cosmos. This is Object 30, a gravitational anomaly of staggering proportions that possesses all the mass of a small galaxy but emits not a single photon of light. It is the leading candidate for a concept that until now existed only in theoretical models, a true dark galaxy, a galactic-scale structure made almost entirely of dark matter, a ghost ship sailing silently through the void with no stellar crew to illuminate its form. The evidence for this object's existence comes not from any telescope that collects light, but from the meticulous mapping of Andromeda's gravitational landscape. Astronomers charting the subtle motions of star clusters and streams within the halo began to notice something peculiar. Their precise measurements revealed that these visible objects were being gently tugged by an unseen force, their paths minutely altered by the gravitational pull of a massive, invisible companion orbiting within the halo. The sheer scale of the perturbation pointed to an object with a gravitational signature equivalent to a dwarf galaxy like the Large Magellanic Cloud, which contains billions of solar masses of material. Yet, when they pointed every available instrument, optical, infrared, ultraviolet, and radio toward the source of this pull, they found absolutely nothing. No smudge of starlight, no glow of heated gas, not even the faint radio whisper of hydrogen. It was a gravitational presence without a physical body, a shadow with mass. This makes it fundamentally different from the ultra-faint dwarfs we encountered earlier. Those objects, while dominated by dark matter, still contain a small number of ancient stars. This candidate appears to be completely barren. The leading hypothesis is that we are looking at a pristine dark matter subhalo that managed to avoid the accretion of baryonic matter, the ordinary atoms that make up stars, planets, and us almost entirely. In the early universe, dark matter is thought to have collapsed first, forming a scaffolding of halos of all sizes, gas attracted by gravity, later fell into these halos, cooled, and condensed to form the first stars. The theory suggests that in some rare cases this process could have failed. Perhaps the dark matter halo formed in a region where the cosmic gas had been heated and ionized by the intense radiation from the first generation of stars, preventing it from cooling and falling in. Or maybe it experienced a high-speed encounter with another structure early on that stripped away any gas it had begun to collect, leaving behind a naked halo of pure dark matter that has drifted untouched and starless for billions of years. Confirming the nature of this object is one of the most exciting and difficult frontiers in modern astrophysics. The primary method remains gravitational lensing. Astronomers are patiently monitoring distant quasars that lie directly behind this region of Andromeda's halo, watching for the telltale flicker and distortion that would occur if the dark object's gravity momentarily magnifies their light, an effect known as microlensing. Detecting such an event would not only confirm the object's mass and position with incredible precision, but could also provide clues about the size and distribution of the dark matter particles within it. Other efforts involve ultra-deep observations with the world's most powerful telescopes, searching for any sign of a handful of stars that might have somehow formed within it, which would at least provide a visible beacon to study. Even the non-detection of stars is valuable data, allowing scientists to place stringent limits on just how truly dark this galaxy candidate really is. The implications of confirming a dark galaxy would be revolutionary, providing the most direct evidence yet for the cold dark matter model of cosmology. It would demonstrate that dark matter can indeed form structures on its own, completely decoupled from the ordinary matter that we are made of. This would be a crucial step in understanding the true nature of this mysterious substance that makes up 85% of the matter in the universe. Furthermore, the mere existence of such an object surviving for billions of years within the gravitational sphere of a giant like Andromeda tells a story about the hierarchy of cosmic structure. It suggests that the halo is not just a graveyard of consumed stars, but a dynamic ecosystem teeming with dark matter substructure, most of which is entirely invisible to us. This single, silent gravitational echo challenges us to expand our definition of a galaxy and accept that the universe may be filled with countless invisible islands, a hidden architecture of dark matter that forms the true backbone of the cosmos, upon which the world of light is merely a brilliant and fleeting decoration. So what does this incredible menagerie of cosmic oddities actually tell us? It reveals that Andromeda's halo is not a static graveyard or an empty void. It is a dynamic archaeological site, a sprawling archive that has been meticulously recording the galaxy's entire history for billions of years. Each of these 30 objects is a piece of evidence, a clue in the most epic detective story imaginable. Together, they don't just show us what's out there, they tell us how our galactic neighbor became the magnificent spiral we see today. Think of the halo not as a simple sphere, but as a vast, three-dimensional crime scene. The evidence is scattered everywhere, and each type of object tells a different part of the story. The ghostly streams of stars, like halo streamer alpha, are the chalk outlines showing us the precise paths of dwarf galaxies that were torn apart by tidal forces. The ultra-faint dwarf galaxies, objects 7 and 8, are the surviving witnesses, ancient and pristine relics that managed to endure the violence. The hypervelocity star and the runaway supermassive black hole are the smoking guns, hurtling away from the scene of a past gravitational catastrophe. And the dark matter clump and the potential dark galaxy are the invisible fingerprints of the prime suspect itself, the mysterious dark matter that orchestrates the entire cosmic dance. This evidence paints a clear picture of a galaxy built through relentless cannibalism and steady accretion. Andromeda did not form in isolation. It grew hierarchically by consuming smaller systems. The halo is the final resting place for these consumed galaxies, but it's also the storage warehouse for the raw materials of future growth. The counter-rotating gas cloud Object 10 is a delivery of pristine hydrogen, the next shipment of fuel for future stars. The dusty starburst galaxy Object 19 shows us that this process of building and consuming is still ongoing even now. The halo is both a museum of the past and a nursery for the future. Perhaps the most profound lesson is that this history is written in light and in darkness. We learn from the stars we can see, like the incredibly metal-poor star Object 27, which tells us about the universe's first moments. But we also learn from what we cannot see, from the gravitational influence of dark matter that sculpts the orbits of everything else. The pure dark matter clump and the candidate dark galaxy are perhaps the ultimate testament to this, suggesting that the luminous universe of stars and galaxies is just the visible tip of a much larger, darker cosmic iceberg. The halo forces us to acknowledge that most of the universe's mass is invisible, silently guiding the evolution of everything we can see. Ultimately, this grand synthesis transforms our understanding of galaxies from simple islands of stars into complex, evolving ecosystems. Andromeda's halo is a testament to a universe in constant flux, where destruction and creation are forever linked. It's a record of violent mergers and gentle accretion, of ancient fossils and newborn stars, all coexisting in a vast sphere that tells the complete story of a galaxy's life. By deciphering this cosmic archive, we do more than just satisfy our curiosity about our nearest galactic neighbor. We uncover the universal processes that have shaped every large galaxy in the cosmos, including our own Milky Way, revealing the beautiful and violent story of how all structure in the universe comes to be. Each of these 30 strange objects, from the ghostly streams of shredded galaxies to the brilliant beacons of dying stars, tells a vital piece of a story written on a canvas billions of light-years wide. They reveal that the halo is not a silent, empty frontier, but a dynamic and bustling archive, meticulously preserving the entire violent, beautiful, and ongoing history of our closest galactic neighbor. It is a realm where the past is not lost, but simply frozen in time, waiting for us to learn how to read its language. The hypervelocity stars, the dark matter clumps, the ancient stellar fossils, each one is a clue in the greatest detective story ever told, the story of how a giant galaxy like Andromeda is built. What this menagerie teaches us is profound. Galaxies are not born in isolation as perfect, static islands. They are living, evolving ecosystems that grow through a relentless process of accumulation and destruction. They are cosmic cannibals, consuming smaller neighbors and incorporating their stars, their gas, and even their central black holes into an ever-growing structure. The halo is the ultimate evidence of this. It is the galactic equivalent of an archaeological dig site, with layers of history stacked upon one another. The pristine gas clouds falling in for the first time show us the future fuel for star formation, while the ghostly streams of completely dissolved galaxies are the skeletons of past meals. This is the hierarchical model of galaxy formation playing out right before our eyes, a process that has shaped every large galaxy in the universe, including our own Milky Way. Perhaps the most humbling lesson is that most of this story is written in darkness. The sheer number of objects that are either completely dark or dominated by dark matter, from the pure substructure clump to the candidate dark galaxy, forces us to accept a universe where what we see is only a tiny fraction of what actually exists. The luminous stars and glowing gas are merely the glittering decoration on a hidden architecture of dark matter, the true cosmic scaffolding that guides and dictates the evolution of everything. Studying the halo is therefore our best way to map this invisible geography, to understand the nature of the mysterious substance that makes up the vast majority of all matter and holds the entire universe together. This journey to the edge of Andromeda is more than just a catalogue of cosmic oddities. It is a fundamental shift in perspective. It challenges us to see galaxies not as simple pinwheels of light, but as the sum of their intricate histories, their visible parts surrounded by a vast and informative shadow of their past. Every time we look up at that faint smudge in the night sky, we can now know that it is surrounded by a sphere of wonders, a realm of ghosts, giants, and cosmic escape artists, each with a tale to tell about the forces that shaped our corner of the cosmos. We would love to hear which of these 30 strange objects captured your imagination the most. Was it the runaway black hole, the lithium-rich star, or the silent dark galaxy? Let us know in the comments below, and be sure to subscribe for more journeys into the deepest mysteries of space.